Prosecution, please read the indictment. The defendant, Rika Sextet, also known as the number 6, is accused of being the lacunary phantom thief, known for stealing notable objects like the equation playground seesaw.
No way! I'm not the thief!
Well, here's the evidence we have so far. The lacunary phantom thief makes their mark by leaving behind an infinite power series with unknown coefficients, along with the message, "Hey kid, you'll never find me with this." This seems to suggest that there is no value such that the function returns the identity of the thief, hence why we refer to this perpetrator as the lacunary phantom thief, apparently from the Latin word for gap or pawn.
Objection! How do we know it isn't a constant function?
Well, we used the function on 2 different algebrailians and we ended up with different values.
Very well then, continue.
Analysis has shown that no matter who we try it on, the function seems to work.
Such an infinite power series that converges everywhere is called an entire function, because it converges on the entire complex plane.
It's taking a while, but so far we found values that equal to these values on the complex plane. As you can see, there's an extremely small gap around the value 6, and we search input values up to 3,417 units away from 0.
Hold it! Are you sure you're showing the entire image for the domain we have so far? Zoom out. Your Honor, what do you reckon that value is?
I'm no maths expert, but it looks to be around 0.5 plus 14.135i.
Oh, I meant 0. Are we seriously gonna keep bumping into this guy? Anyways, it seems that this circle is even smaller than 6's.
Well, that doesn't rule out 6 from being the lacunary phantom thief. Even if 0.5 plus whatever that number is does turn out to be a lacuna, how do we know that's not a red herring? For all we know, there may be 2 lacunas and the other one is 6.
Objection! Introducing Lil Picard theorem. If a function f is entire and non-constant, then the set of values that f of z assumes is either the whole complex plane or the plane minus a single point. The minus a single point part is necessary as the example f of x equals e to the z shows.
That can never be 0. Objection! Negative infinity. Whatever, you still need to convince me.
Convince you I can. First of all, the points don't have to be 6 and that remains 0. Suppose f of z is an entire function that omits 2 values. Now let's take this new function which will become our new f of z. All it does is shift and stretch the function. But when f of z equals z1, this new f will be 0, and when f of z equals z2, the new f at that point will be 1. Let's work with this function for now. Now, for those who watched the previous sum video, you may remember that every point besides 0 has a complex logarithm, so let gz be equal to 1 over 2 pi I log of f of z. It's more accurate to say that g is a function such that f of z equals e to the 2 pi I g of z.
I don't see where you're going with this.
Well, since f of z can't equal 1, e to the 2 pi I gz can't equal 1 either, and e to the 2 pi I n only equals 1 if n is an integer, as demonstrated by the unit circle.
So you created a new function that cannot be an integer, so what?
We create another function h of z such that gz equals cos hz.
Doesn't that make the range only between -1 and 1?
In the real numbers, yes, but we're not in Hokkaido anymore, Toto. We are in the world of complex numbers, and in the complex numbers there exists a value of z such that cos z equals 2. Infinitely many, in fact. However, g of z cannot equal 2 as it's an integer. So when is cos z an integer? You remember that cos 2 pi n equals 1 for all integers n, right? In the complex numbers, you need to tack on this at the end, where this is the inverse of the hyperbolic cosine, which is defined with e to the zeta plus e to the minus zeta over 2. Also, m is also an integer, can't forget about that. We are in the home stretch. First, I want to introduce Landau's theorem. If f is a holomorphic function...
Holomorphic?
Oh, forgive me. A holomorphic function is a function defined on the complex plane and can be differentiated everywhere it is defined. An equivalent definition for an entire function is that it's a holomorphic function defined on the entire complex plane. Anyways, as I was saying, if f is a holomorphic function and the unit disk with the property the absolute value of f prime of 0 equals 1, the radius of the largest disk contained in the image of f must have a radius greater than 1 over 72.
Why is that specific number?
That's a story for another day. Now, suppose that there is a point w such that h prime of w does not equal 0. Now consider the function, we're running out of letters. Aha! Capital H of z equals 1 over the absolute value of lowercase h prime of w, r, times lowercase h of z minus w for some number r. The largest disk in the image of capital H must have a radius greater than 1 over SoME4, so the largest disk in the image of H is at least the absolute value of lowercase h prime of w, r over SoME4. If we make r big enough, we can be sure that we can cover at least one point that fits this formula, no matter where we place it. However, we already proved that h cannot equal those values. Therefore, the only other option is that h prime of w equals 0, meaning that h is constant and then f is constant. QED.
I completely lost track of what you just said, but that is a convincing argument. You said that was the little Picard theorem. That implies that there is a great Picard theorem.
Yeah, let me just flash it on the screen. An essential singularity is a point W where neither the limit of f of z or 1 over f of z at that point exists, and a punctured neighborhood is a region encompassing that point but does not contain it. The proof is a bit more complicated, but it does imply the little Picard theorem. A link is in the description. Hey, I just received a note. They just found a value of z such that f of z equals 6, somewhere around 3,417 plus 1,119.181 for I.
Oh yeah, I forgot that was what we're trying to do.
So, does that mean I'm innocent?